leaving sputtered beads behind. And I invite people to sort of roughly do some rough calculations on the back of the envelope and imagine that you have a cylinder of palladium that's 10 microns in diameter and 10 or our total target's only 100 microns thick. So it's maybe 10 or 20 microns, a cylinder 10 microns in diameter and some tens of microns deep. And work out how much energy it takes to melt and inject that material. I think you'll find out it takes millions of fusion events to do that. Some of the events don't produce those smooth sputter beads. It's not a very good view graph, but some events produce very smooth cratered areas. It looks like to us, our interpretation of this is that this material ejected in a gaseous state. So instead of using just the heat of fusion for the palladium, for that one you might use the heat of vaporization for this one, and work the numbers that way. So we have also recently conducted a good initial survey using SIMS analysis at Lawrence Berkeley Laboratories at the National Center for Electron Microscopy, studying both the titanium and the palladium systems that we have. And we have looked at every mass unit from 1 to 250 and charted isotope ratios. And we have seen some distinct shifts that look mysterious to us in those isotopic ratios of a number of the elements. We need to revisit that work, and we're kind of a low-budget operation. We only get access to that equipment when someone's generous enough to let us in the side door. However, we're hoping that will change sometime soon. However, so I'll leave you folks with one of the mysteries that we saw in the SIMS. And we need to repeat this with higher resolution time of flight SIMS. We looked at titanium as a trace constituent in palladium in our material, and we looked at sites on our material. Since we have an ice-melted material, we can go and find a region that was extremely hot and affected, so we might say it's more reactive than the average site. And there are 5 isotopes of titanium, and there's 4 of which are at roughly 8%, roughly a few percent, and 1 of which is about 10 times more. And in the SIMS study, we look at the ratios, and in the before sample, we did indeed see the isotopic ratio of the 5 titanium isotopes being exactly as predicted. However, in the sample in the exposed sample, we looked at the peak 48 had swapped positions with peak 47. So, since this is a scientific conference and we're supposed to share ideas and benefit from your knowledge and experience, I invite you to help us solve this mystery of where how this might have occurred. And with that, I guess I'll open it up to questions.
Thank you, Russ and Roger. This paper is open for discussion.
I have a question.
Actually, the bubbles, the collapsing bubbles, are a very good injection mechanism for loading the deuterium into the metal. However, sometimes we do preload the metal by just using gas load, just exposing the palladium to deuterium gas. Yes.
Two remarks. The first is, why is cavitation the same thing as cold fusion? Well, there is a possible answer. Would you project your third picture, the box? of a few watts, say 10 watts, then what we want are reactors of about 2 kilowatts. So, all right, the factor of 100 into energy of the acoustic discharge is nothing to gain. So this is a very nice path to overcome some trouble of electrolytic cells.
You know, I forgot one thing when I was mentioning to my Italian friends who have looked at neon. We also looked at the neon 22 in our helium, and we found it below the limit of detection in the system, and it would certainly have been present where this helium atmosphere is.
Let me show you a pattern in titanium with a photon again. I'm an ultrasound engineer. This phenomenon is well known to the ultrasound engineering community since from some 10, 20, 30 years ago. The metal will melt when captivated. So is this the same phenomenon which we have been experiencing so long time ago, and you are reproducing it again?
Well, actually, we looked, consulted with a lot of ultrasound experts and people with cavitation damage. No one has seen these kinds of molten ejecta phenomena. However, we did find one location where we find this identical phenomenon, and some of the people from the theoretical division at Los Alamos dug this up for us. They wouldn't share the papers and the pictures with us. They were classified. They could report it to us, but they couldn't actually give us hard copy. This phenomenon is seen on californium foils when they undergo spontaneous fission. And it clearly requires a nuclear scale of energy within the metal. You have a thin 100-micron sheet of metal heat sunk in a circulating fluid. It's very difficult to produce such events through other forms.
Californium, you mean the fission?
Yes.
Okay, so that point is very, very important for our understanding from the ultrasound engineering community. Appreciate to clearly indicate what's the difference from historical phenomena to UFO phenomena.
Yes. Thank you.
Next paper will be presented by Professor Kasagi, energetic proton.
I'd like to discuss the result of our experiment, and I just changed my title from the original, just say on the various metal plates, not just I want to concentrate on the result of titanium. But so from the just after 1989. We concentrate on to see the nuclear reactions induced by very low energy neutron bombardment on various metals. So in that sense, our study is just the traditional way of nuclear physics, because we are using the energetic particles to impinge it to the titanium metals. So the first, we put the two aims for our studies. First one is reaction rate of the D plus D reaction in titanium at very low energy, whether the reaction rate really changes or not. And for example, if we lower the instant energy, of course we can expect that the electron screening effect cannot be neglected, and also the neutron density effect might be other than usual D plus D reaction in the metals. So we look at the reaction product by bombarding the 100 keV neutrons for a long since then. I already showed some of the part of the result in the first conference at Nagoya and also at Maui, but I just tell you again how our experiment was performed. So that this is just all nuclear physics experiment by using the Cockcroft-Lawton accelerator at the Tohoku University. So we have the accelerator has the RF ion source, and the beam was accelerated by this accelerator and got let's say something around 100 keV neutron beams. In order to separate the atomic beams, we put a dipole magnet before the target. Instead of the usual nuclear reaction studies, we use the very thick target like deuterium titanium or titanium plate or platinum plate. And in order to look at the reaction product, which is emitted in the target during the bombardment, we put the silicon detectors at the backward angle. And in order to separate, identify the particles, we use the delta E particle identification techniques for the typical detector for the let's see. Delta E detector is something around 20 micrometer or 10 micrometer to the big one is 1 millimeter silicon detectors. So this is the spectrum, proton spectrum, which was observed, let's say, sometime maybe 3 years ago. What surprised us from this spectrum is this sharp peak is just corresponding to the usual D plus D reaction, makes up 2.7 and maybe protons. For the detection angle is, let's say, something around 130 degrees. And beyond that, we could see the lots of events around here. That's the first surprises for us, and we can let's see. So this huge peak is corresponding to the usual reaction, and of course the counting rate is so high, so that the detector can pick up the 2 pulses within the time, resulting time of the detection system. So this is the so-called pile-up peaks, double even pile-up peaks, and just corresponding to the pulse height is just twice of the single event. And also we can see the triple pile-up events around here. So beyond that, if we have a further pile-up event, that should be the order of around here. So we are very sure this is a real event. And that time established, then why not the simultaneous reaction process like a D plus D plus D makes a proton plus neutron plus alpha. So let me show you the Feynman-like diagram. The first one, this part is corresponding to the green broadband. In the first stage, neutron interacts with the neutron and makes a herring tree, which is running through the target and can react another neutron, makes a high energy protons and also alpha. So the first step reaction, we have a 3.3 MeV values, and the second step reaction, we have a 18 MeV values. As I showed you, in this spectrum, the continuum part energy of the maximum energy of this continuum part is higher than this sequential process. So we have to think about the other process like this one, because if the free neutron interact simultaneously, then we got another Q value because these are the Q values added together to this one. So then we got a little bit more higher energy protons instead of maximum energy of a sequential reaction process. But anyway, we have to convince you to see. I get the rough idea why the sequential reaction makes a broad peak, because the first step, the neutron in the target, this is a real target for the reaction, and the beam hit to the neutron, and helium-3 is like a beam for the second step reaction. But in this case, the helium-3 goes various directions, and also the duality passing through the titanium, it loses its energy. So that is, in this case, the second reaction is bombarded with the various energy of helium-3. These two makes up the broadband. And also the yields of this sequential reaction process is we need two neutrons in the target. So the yield should be proportional to the density square of the density of neutron in the target. So that if you divided the yield of that map by the usual one-step reaction, then you can get a rough idea of the density of the neutron inside the titanium. But anyway, we just make a calculation for the spectral shape of the sequential processes. And to get so this is just a high energy part of the proton spectrum, and we change the detection angles, let's say from the 110 degrees to 155 degrees, and the calculation of the two-step sequential reactions reproduce the experimental data very well if you assume the continuum background. For the simultaneous 3D reactions, D plus D plus D makes a proton plus neutron plus alpha. We have started just a simple assumption because we don't know the real mechanism of this process. So the simple assumption makes for example, the proton spectrum should follow the phase space of the final state, phase space of protons. And also, I have to remind you that we have alpha particles also, because our reaction should make three particles in the final state, neutron, which happen to be observed in our system, but alpha and proton, alpha particles and proton should be observed. Therefore, we did a measurement of the alpha particle by using, as I told you, using the delta E technique. And here, we clearly see the locus for the alpha particles. So this is the vertical axis corresponding to the delta E, and the energy lost in the delta E detector, and this horizontal axis corresponds to the energy deposited in the E detector. And actually, the spectrum of these alpha particles just follow the like a phase space for the D plus D plus D reaction. And in this case, unfortunately, the delta E detector, thickness of the delta E detector limit the observation of the minimum energy of alpha particle. So that if the sequential reaction process exists, we should see that this type of shape around here. And after that, we continue this. After that, we measure the instant energy dependence of this alpha particle events. Because in this energy region, reaction rate more or less proportional to the penetration factor, because we are using a very low energy neutrons. So, for example, the yields of the first usual reaction just follow the penetration factor for Z plus Z equal 1 reaction. And how about the alpha particles? That's our question. And this is the ratio for the yield ratio for the alpha particle to the proton from the D plus D reaction times 10 to the minus 6. So the instant energy dependence is more or less flat. But if you assume the target charge like a Z equal 3, then this curve should go this way. So this is and if you assume that target charge is like Z equal 2, then this should be followed this blue line. I can say that the blue line is more or less reproduce the experimental results very good. That means that actually the instant neutron see the two hypothesis target in the titanium. Okay, I have no time to. But this phenomena can be observed only for the titanium target. That's our next question. So we bombarded a platinum metal at the instant energy of 100 case, this is a preliminary analysis though. I just give you a rough number. For the titanium case, for the platinum case, this ratio is about 1/3 of the titanium case. That means density in platinum, neutron density in platinum is, in the average sense, something around 1/3 of a titanium case. And now, for the three-body reaction product, for example, continuum proton, yield of continuum proton divided by the, let's say, usual reaction process. For the platinum and for titanium, this is not the same as this one. This is just 1/6 of this 1/6. And for the alpha particles, the number is more or less same for the continuum proton case. That is actually the smaller than the 1/3 case, 1/3. So that means this process depends on the neutron density more strongly. Anyway, maybe I have to stop around here. So I just summarize. For the proton spectra, we observe the broad band around between 12 to 16 MeV, and it can be completely interpreted by the sequential reaction process. And the ratio of this yield is something around 10 to the -5. That means the atomic ratio of the neutron to the titanium is something around 1.5. And for the continuum part of, we saw the continuum yield for the proton spectrum up to 17 MeV, and also in the alpha particle spectrum just up to 6.5 MeV. So this observation strongly suggests that the simultaneous reaction process might occur in the bombardment. This D plus D plus D makes alpha plus D plus N. And for the yield of the alpha particles compared to the yield of the normal reaction process, we measure the incident energy dependence of this yield, and the result supports this interpretation again. But the difficulty is this yield is just 10 to the -6. So that means three-body reaction is anomalously enhanced at least 10 to 10. Thank you.
Thank you, Professor Kiseki. And in the interest of our time and our coffee break, I'm just going to take one question from Michelle.
Could you tell again what is a proton according to you, and what is a 16 MeV proton? What do you call 16 MeV?
16 MeV.
How do you get this number, and what is a proton according to you?
We calibrate the detector by using the American alpha, and also the calibration can be done by the spectrum itself, because we have a proton from a C plus D reaction and the parallax peak, so we can easily calibrate our detector.
Do you know the charge of the particle? Will it be negative charge?
Well, what do you mean the negative charge?
Electrons.
No, never.
Why not?
Oh, because after that, yeah, if you compare the spectrum measured with a thin absorber and a thick absorber, we measure the energy loss, energy difference, actually observed energy. So that just corresponding to the proton.
You have a thin silicium, and you get 16 MeV from a single thin silicium, silicon detector.
Yeah, and no, I mean the thick detector. In this case, okay, I didn't tell you in detail for the experimental technique, but we use the 2 millimeter silicon detector to measure the high energy protons. So it can go, we can measure
following low discharge experiments. And this work is done in scientific and industrial station, which Russian Federation and with support of company. After a few years of work with low discharge, it was found that there can be identified two types of events. One of them is existence of some mechanisms of transferring energy flow from low energetic ions to high energetic nuclear particles. And the second mechanism is this nuclear reaction itself. In this case, to conduct this research experimental installation include itself few types of detection. This is a vacuum chamber with volume of 10 liters. It illustrates the cassette holder and cassette. Were possible to install different samples from different materials, palladium, plutonium, niobium. And experiments were running in atmosphere of hydrogen, helium, argon, xenon. This is neutron, helium-3, neutron moderator, gamma detector, germanium lithium gamma detector, X-ray detector, silicon lithium X-ray detector. This is two channels detector, silica, gold silica to detect heavy particles. And it's followed by foils, different things. Also was used Röntgen film, which was placed inside the chamber as well outside. The thickness of the chamber wall is 5 millimeters. This is gamma measurement.
Регистрация гамма излучения производилась на американских.
Monitoring of gamma radiation was performed in separate devices. Separately was monitored background during days. And this part of measurement monitoring was shown by this points illustrate gamma emission experience itself. Also after shutting down low discharge. So here is shown that we can see gamma emission for the system palladium, palladium system, palladium hydrogen system. High current density for milliamps and low current density, and also in palladium argon atmosphere, which significantly increases above the ground. This axis represents calculated 4P они получены вычитанием рабочего спектра background. The spectrum were obtained by extracting from a work spectrum background. The specific spectrum given after shutting down flow discharge. This is Mallove, zirconium, and this is Conwell experiment with silver. And we can see that here is no already above the ground. Similar spectrum represented in this picture and for different systems. However, silver cathode in hydrogen atmosphere shows some spectrum above the ground. Specially developed software attempt to simulate decay changes. And it was counted all changes exist lines of sequence transformation. During the experiment, it's possible to monitor the short time living chains. After experiments, it was monitored radiation from isotopes for a lifetime of a few hours. Some of the caches can give some radiation. Lift on the ground was measured by helium 3 The average level was 10-15 liters per second. And after finish of experiment, neutrons were observed about half hour. This is a silicon detector with different thickness of foils. 10 microns and 80 microns. We can see the shift of energetic spectrum where foil is more thick. According to track distance, it's possible to detect lithium and boron. This board shows electrical measurement. During low discharge, we can observe both current pulses, which not depend from electrical supply system and are not processes generated inside plasma. And front of this impulse about 35 nanoseconds. This is spectrum. This is spectrum of such electrical pulses for different materials and gases. Measurement was conducted by Röntgen film. Different equipment with different types of moderators. And this is a result of such kind of exposition. It's aluminum foil of 100 microns thickness. For palladium cathode, this moderator partially allows to go radiation, or на aluminum cathode they were completely absorbed. So we believe that this is the result of electron views. Because exposition registered only when behind film is lead plate. In the case of zirconium cathode, discharged hydrogen and argon shows exposition behind chamber wall of 5 millimeters thick. This is picture which is also in case when behind film was installed lead shielding. And this experiment had perfect reproducibility. When different materials were compared, we found a correlation. Major nuclear level cathode materials, 30 Kelvin completely absorbed by aluminum foil. For palladium, we can see partial absorption, partial penetration. In the case of zirconium cathode, we can see exposition. And this even seems like solid state electronic laser. Probably exists some kind of mechanism where non-elastic collision between nuclear particles and not elastic. In the World Conference, we reported different types of reaction between excited palladium and deuterium. It's possible. Fusion reaction, fusion reaction. This reaction which gave clean product, non-radioactive product. And the reaction which gave dirty product. Very good. Thank you very much.
Of this particular session. As I said on Monday, we have been running this, we intended, and we have been running this as a single stream session. And one of our problems was that we had a very large number of contributions in the theory and modeling session. And really, for us to have had any sensible discussion, a presentation of this as an oral program would have taken 2 days, and we haven't got 2 days. So we decided that we would only give, have a very limited number of oral contributions, which is not intended in any way to be a reflection on those people who have produced excellent posters. And that we would instead aim tomorrow, after that Peter Harrison kindly agreed to say something about his work and to introduce a discussion of the posters. Now, we haven't left a great deal of time for the discussion of the posters, but I thought it was better to proceed that way and let us see how people respond, and if they wish to have more time for the discussion of the theory in the theory section, and let us see whether we can accommodate that in some special way. Now, you will see that our first contribution to this session, the first contribution, is by Giuliano Caparata. And I will just say a few words about how that took place. Giuliano Caparata is a quantum field theorist who's worked in quantum field theory from everything from quantum chromodynamics to quantum electrodynamics. And this is perhaps something, Giuliano, if I may say that, which is not always very well appreciated by the scientific community as a whole, and nor even by those who should appreciate it, the people who are working in the field of theory. And what tends to happen is that when somebody speaks about something in any field of this subject, and in theory in particular, other people set up their own framework, and if you then do not conform to their framework, you get criticized. And I view the criticism which Rabinovitz and his colleagues presented after the Maui conference very much in that light. And I believe that you should re-emphasize, in asking you to come and make this presentation, you should re-emphasize the essential parts of the quantum electrodynamical approach to this topic. And if people want to criticize Giuliano, I would urge them to do so within the framework of quantum electrodynamics and not within the framework of perturbative quantum mechanics. Giuliano.
Thank you very much, Martin, for giving me this opportunity, not so much to respond to the criticism of that particular group, but in fact, as you suggested also, the title of my talk, to try and set cold fusion in context. This is something that I'm very keen on doing, because I do believe, and I hope after this talk, this belief will also be of some of the people here, that we do need a very clear understanding of what are the implications of cold fusion, and perhaps this might be very useful for its progress. Because it is my feeling that we have been rather slow in progress, just because the investment in understanding what the meaning, theoretical meaning of cold fusion is, has not been very big. So these are the things I will talk about during my talk. First of all, I will take up the pathology of the science of cold fusion and show why is this a pathology to most of our colleagues in the scientific community at large. Then I will show how the change of paradigm, which I'm trying to foster through an approach which takes into account the coherent properties of QED, in fact cures such pathology, and then I will end up somehow in the framework I've been discussing to give a reply to the critiques of my critics. Now, it's already 6 years from that spring day of 1989 that cold fusion is with us, and in spite of its progress, which is certainly undeniable, even, the first the first part of this conference has been a good example of this, is still a heresy. Well, you may ask why, and people are economic interest, are again confusion. Yes, but this doesn't explain a heresy. Contemporary science, is that service or economic interest? Yes, but how can you stand as a heretic for such a long time? Actually, I think cold fusion is still a heresy, and of course it's also called pathology, because it's basically heretical. And that is, it's totally against the expectation of the paradigm. Instead, therefore, of condemning in a moralistic way most of our colleagues for their, what we call unreasonable, what we think a reasonable attitude toward cold fusion, I think we should try and put ourselves in their shoes. Now, let's take a normal scientist in the sense of Kuhn, an appreciated member of the scientific community, and let him look at the cold fusion panorama. And what does he see? Essentially, he sees a set of monstrosities of this form. Now, we know that the deuterons go to the octahedral sites of palladium, and the expected fusion rates are 100 orders of magnitude smaller even for the D2 molecule, because, you know, over gamma of amplitude, the tetrahedral sites are much far away, further away, 2.8 angstrom instead 0.72 angstrom. And in fact, we already know there are very good calculation by very good expert, that the amplitude for transition are ridiculously small. Okay, now, even admitting that maybe there's something else which we don't understand, let us admit that these two deuterons fuse, so they must do so according to this, which is very well known to happen every time the D2 molecule, the two Ds fuse. They have to go 50% into those channels. 50% and 50%. And whereas the cold fusion phenomenology, which is reproducible and reproduced, gives the famous N over T ratio of that type. And in fact, we know now that the main fusion path is through helium, 4. Oh, by the way, I haven't, I'm going to go through the Coulomb barrier, but not through the PDD barrier, in the sense that I'm not going to discuss any other aspect of cold fusion. I'm only taking the original Fleischmann-Pons system. So, why are these monstrosities so monstrous? Because I made a statement, let me now explain why. Because they're a fatal blow, as I said, to the paradigm. And the paradigm, let me remind you, is a set of generally accepted ideas, dreams, expectations, theories, even the organization of the scientific community. So it's something very, very strong. And this paradigm is rooted on the fundamental notion, even if nobody says so, but actually it's a property of the theory, which is behind the paradigm of asymptotic freedom, which means that particle interaction vanish when probed at space-time distances which are much smaller than the typical space-time scale. In our particular case, we have a particle interaction at the nuclear scale, which is 6 orders of magnitude smaller than the scales of the lattice. So therefore, for two particles that fuse inside the palladium lattice doesn't exist. It's just the same as the vacuum. In other words, the two deuterons at that scale are essentially asymptotically free. They are free from the dynamics of the lattice. So they must fuse in the same way as they do in vacuum. Okay? And so the scales are different, so they cannot mingle with each other. They cannot interfere with each other. So the lattice can in no way interfere with fusion. Thus, no theory of cold fusion phenomena can be built within the paradigm. And this is a theorem. And everybody trying to do this would just be like a person who's trying to construct a perpetuum mobile, knowing that there is the second principle of thermodynamics, which denies it. I can prove the theorem that any quantum field theory which has short-range interaction must be asymptotically free. I mean, this has been done in QCD through the renormalization group, which is where, in fact, this notion has been introduced first, and now this can be extended without any problem to the QED that is looked at within the paradigm. So I think the pathology of cold fusion is unavoidable if one does not want to go beyond the paradigm. Thus, well, the pathology of cold fusion is really in the eye of the beholder. Okay, so this is the point. Let me now try and show you how you can cure the pathology through the necessary step that one has to take to use correctly the laws of nature which are already known, and that is QED. Now, the paradigm uses only the electrostatic part of QED and builds a picture of matter which I've called the electrostatic mechanism. Well, in America it's the erector set, okay? Where you essentially assemble the pieces of condensed matter, the fundamental pieces of condensed matter, through electrostatic bonds of any type, like, you know, the covalent and whatever, okay? So the point is that the electrostatic mechanism is unable to yield any explanation of cold fusion because it is asymptotically free. So there's no way of really squaring up within the electrostatic mechanism to the PDD system that has been first studied by Fleischmann and Pons. Because it is very clear, and this has been shown in a paper which Martin, Stan, and I have published in Nuovo Cimento, that the phenomenology, which is now established, and I take it as established because it is, requires a large amount of long-range order that the nuts and bolts of the electrostatic mechanism can in no way guarantee. And the fact is the electrostatic mechanism, in fact, it is very loose because of the Heisenberg principle. It's very loose because there are fluctuations, essential fluctuation due to the requirement. Localization requires also a large momentum spread, and that is called the Heisenberg principle. Let me now show, in fact, that this kind of long-range order, which is present everywhere in the phenomenology of cold fusion, and in fact is also present everywhere in the phenomenology of condensed matter physics, does require the doom of the paradigm and a radical new approach. For if you ask the question, what is a piece of condensed matter? According to the paradigm, it is a macroscopic set of elementary constituents, atom molecules, which are held together by the loose nuts and bolts of the electrostatic mechanism. They perform the zero-point oscillations around the position of stability, and the zero-point oscillation that, as I said, is prescribed by the Heisenberg principle. And they make this zero-point oscillation together with the ether oscillators, which are a good representation of the quantized electromagnetic field in what is called the perturbative ground state, PGS. Now, the approach that I'm trying to foster, and without really changing at all the laws of the fundamental laws of the standard model in the QED sector. Just this new approach just tries and recognizes, in fact, there's a missing element in this picture of the electrostatic mechanism. Actually, I'm happy to announce you that in a couple of months, World Scientific will publish a book, a general book at the graduate student level on this approach, showing in fact how the full quantum field theory of the standard model sector QED, in fact, is at the basis of these deductions. Now, for this approach, the ground state, it is a laser-like state where matter and field, which finds itself now not in the perturbative ground state, but in a classical configuration of large amplitude, they oscillate in phase on a frequency or set of frequencies which are characteristic of the particular atomic molecular species of that particular piece of matter. There are two fundamental differences, however, with the laser that everybody knows and cherishes. And that is the laser-like state, being the ground state, is accessed spontaneously without any pump nor the need of an optical cavity. And this happens below a critical temperature, Tc, and above a critical density, rho c. This spontaneous access, in fact, gives rise to the phase transition. Therefore, number two, no electromagnetic radiation leaves the system because it's in the ground state. Because if it did, that would violate, of course, the principle of energy conservation. Now, what are these values of Tc and rho c? Now, if you look and analyze the system, quantitatively, you find that with the couplings and the densities, with the couplings to the electromagnetic state and the density you have in condensed matter, you have, in fact, that normally the densities of the order 10 to the 22, 10 to the 23 centimeter to the minus 3 are bigger than the critical density, and the critical temperature lies around 10 to the 3 Kelvin for most systems. So these states, which I would call the coherent ground states of matter, are thus very frequent in matter. Now, the most counterintuitive, and this is one of the problems which has most of my credits completely lost, I believe, because it's very counterintuitive, of the coherent ground state, is that in the coherent ground state, both matter and the classical electromagnetic field are in an excited state. The negative interaction energy between these two systems, in fact, does overcompensate because of the minimum principle, does overcompensate the excitation energy. So if one looks at these two systems by themselves, they have very peculiar features. They have not the features that you would expect of an object which is in a state of minimum energy. Okay? And this, of course, depends on the fact that the electromagnetic interaction is a long-range interaction, meaning the transverse electromagnetic field, and therefore this happens in macroscopic pieces of matter. Now, in the coherent ground state, different from what happens in the perturbative ground state, where, of course, asymptotic freedom is the law, in fact, asymptotic freedom is in principle invalid because the system is a collective system. So any argument which is based on the particle interaction, on the individual interaction, of course, is based on a delusion, because now the system is a whole, and as a whole interacts with the thing that come out from the outside most of the time. So, in principle, therefore, in this new approach, the pathology is cured. But how about in practice? Well, in practice, you have to really look at the problem in detail, and as far as the PDD system is concerned, and the cold fusion phenomenon, but also not only the cold fusion phenomenon, but only in the loading behavior, which is already very strange, and this has been emphasized many times by Martin Flash and Stanley Pons, and we do emphasize this in this paper we have written together and publishing at the beginning of last year in Ho Chi Minh. One needs understanding, for instance, problems like the PD loading at high X and the cold fusion phenomena, the two classes of phenomena at high X as well. Now, the way the theory, QED coherence in matter, goes about explaining or attacking this problem is in terms of the collective system that you do find in the PD lattice. And this collective system, we can call them, actually, in a rather correct way, I believe, as plasmas. Because there are several actors in this kind of drama of the PDD system, and these plasmas, and these actors are the PD ions, which form a coherent plasma in the lattice. The coherent plasma means essentially that these PD ions are just charges which oscillate around equilibrium positions, and they do form a plasma, because this is what a plasma. It's only not an ideal plasma, but it's a plasma which is somewhat confined in certain positions. However, it is exactly from the fact that these charges oscillate that they do hook onto a particular electromagnetic mode. And this mode, and it is from this interaction of the electromagnetic mode and these charges that results a coherent state of the type I've just described, and that I will call a coherent plasma. There are other actors in this drama, and that is the d electrons, which also form a coherent plasma. Now, of course, I've been taken, to say that I really. Oh, by the way, what is a real sign of an idiot? An idiot is a person who undervalues the interlocutor. Now, how can one person think that when I look at this thing, I write shells on this point, that I do believe that the electrons are precisely, the d electrons are precisely in this shell? Of course, there are the quantum mechanical, let's say, dispersions. There are always, and of course we have learned this thing. I'm doing this profession since 30 years. I should know, right? And yet there are people say, this is wrong because doesn't he know? This is wrong because doesn't he know? And this is the drama of cold fusion. Because instead of really picking on the real important issue, we're just nitpicking in a stupid way, okay? And this is happening at posters around and so on and so forth. Anyhow, so I'm just taking a face of a face-centered lattice. These shells are the d electron, then the s electrons, the conduction electron. Of course, they're not s electrons because they are hybridization. I know, but it doesn't matter, okay? If you want to understand the system as complicated as that, if you do this simplification, it's just because otherwise, if you go around all details, you'll never go to the end. And in fact, it's very clear, because nobody understands how to go to the next step, just because they stay on details, okay? And this is, okay? Now, the energy gain due to the coherent process is in fact the raison d'etre for this peculiar and complicated configuration. Now, when the deuterium manages somehow, and we see below, to enter the PD lattice, it forms also another coherent plasma in the particular stability position where it may find itself in. Now, we do know that in the beta phase, the stability position are the so-called octahedral sites, okay? And this is a beta plasma. And this was predicted by the fact of cold fusion. There must be other positions where, and in fact, there must be some phase transition. Yesterday, Celani was talking about this gamma phase, and in fact, this gamma phase is, I think, a prerequisite for cold fusion. And this, in fact, this gamma phase has to do with the plasma oscillation of the deuterium in kind of a disc-like position, which comprise what I usually call the tetrahedral sites. Okay. Now, the realization of one of the phase or another depends on the chemical potential. A rough calculation gives this structure for the beta phase, this structure for the gamma phase, and then you see that there is a transition in terms of energetics about some x0, that for the hydrogen is about 0.8, a little bit smaller for the deuterium. Now, and when you have this transition, of course, you do expect, on the basis of definition of the diffusion coefficient, and that you do have a kind of discontinuity in the diffusion coefficient, and I think there is some evidence for this from a paper which has been published in the Journal of Electronic Chemistry by Mengoli and his group, and I think also in some communication at this conference. Okay. Now, therefore, we have, as far as the PDD system and cold fusion is concerned, there are two questions, and one has to give answers to, and that is, the first is the loading, and the second on the cold fusion phenomena in highly loaded PD. Now, in the Maui conference, I was sort of listing a set of questions that are the most, in terms of phenomenology, are the most natural to ask. The first one is why and how does the process D2, DD to the lattice proceed? This is just the first step for gas absorption. Then one D is on a lattice. Why it exists on a separate state, in an ionized state, like in fact implied by the beautiful experiment of Alfred Kern and electron migration. Why is the plus so mobile at high x, as shown by our Padova friends? What are the phases? By the way, around x equal 0.8 upon 9, you do have something, you know, the proton moves in palladium faster, even faster than in water. Can you imagine that? But that happens, okay? What are the phases of the PDD system? What happens during electrochemical loading? Why ionocells heat after that? And there are many other questions, but these are just a pretty good set of questions. And as far as the cold fusion, is concerned, the other question I was asking in Maui, and in fact, you know, I'm going fast about this because I have nothing more to contribute to this, and people who really want to look at the thing in detail, just they can just look at the proceedings which have now come out. How can one overcome the Coulomb barrier, which is there? No matter, no question. People think, but this is a wave system, so on and so forth. So they even think that the charge now is diffused. But the charge is diffused in the sense of quantum mechanics. But, if you want to make a helium, you better have the charge converge at distance of the order of 10 to the minus 13 centimeter, because that is what the nucleus is of helium-4. And there's so much evidence about this that, again, the problem is we cannot, in order to explain cold fusion, unexplain some 60 years of nuclear physics. Now, those data are there. And the people who collected them were no idiots, even though we find them now on the other side of the barrier, the other side of the camp, okay? All right. So we would like them to be idiots, but they are not. And this is our problem, okay? Because we have to ask, we have to really go through rigorous science, okay? And now let me recall the answers of this. Okay, so you have the molecule come out. Oh, this is a beautiful. How can you put these big balls for deuterium? Don't you know that deuterium has 10 to the minus, has the radius of 10, about 6 or 7, 10 to the minus 13? Yes, I do. I even teach it. But when I make a drawing, if I have to do it in scale, you wouldn't see it. Okay, fine. So, but this is the kind of criticism that I'm taking all the time. And I'm appalled, I'm amazed, but that's it, all right. Let's carry the cross, okay? Oh, by the way, let's carry the cross. I mean, Good Friday is close, okay? All right, so they get to the surface. Here they find the evanescent field, the evanescent tails of the coherent electromagnetic field, which oscillate. There are enormous dispersive forces, therefore the enormous tunneling amplitude for breaking this thing without energy expenditure to break the system, the D2 system, into its component, and then to have it there. Now, what happens, whether the deuterium with their electrons will go inside depends, of course, on the chemical potentials of the gas phase as compared to the chemical potential of palladium. All right. Thermodynamical equilibrium. So you calculate them, and then you see how much deuterium, and if you do a good calculation, you will get some 0.6 or something like that will go inside from the gas phase. And if you don't do anything else, that would be it. And bye-bye cold fusion. That's the trouble, that's the problem of Martin Fleischmann and Stanley Pons. They have taught us how to go beyond, okay? Now, why D plus and E minus just go one for each one in their own way? Because they belong to different systems. And there's energy gain. And there's energy gain to divorce. All right? I don't know whether that's always true. But, okay? But if you do it, then one goes to the electron plasma, the other goes to the deuterium plasma, and they stay well in this way. And Kern has shown that this, in fact, happens. Because this would be totally ununderstandable if you had the molecular atomic approach to the system. Because the Coulomb energy, the Coulomb attraction is always there. Whether you are inside palladium or outside of palladium. So what happened? So this means that outside of palladium, something has to give away. Something has to happen. And it does happen. Alfred Kern has shown it. Okay? Now, the D plus are so mobile because at very high X, the chemical potential shoots up. Positive feedback. Martin Fleischmann has shown it. Okay? Fine. So we are really connecting completely different. Are they really completely different? No, if you don't have. Yes, if you don't have a unified picture. No, if you have the correct unified picture. And here you see a correct unified picture to come out. Okay? Coming out. Now, in particular in the gamma phase, the gamma phase, let me recall you, is where the deuterons go to the tetrahedral side, to what I call the tetrahedral disk. And actually, the existence of this gamma phase was predicted on the basis of the fact that otherwise you wouldn't have cold fusion phenomena. And now this is very interesting, that now cold fusion becomes a means to make you understand solid state physics. Amazingly, in fact, if something happens, if some cold fusion happens, this means, in fact, that there has a very strong and deep implication for the structure of the solid state, of the condensed state. So, if the D's are in the beta phase, then they're too far away. The tetrahedral size can accommodate more than one D, a thing that is almost impossible for the tetrahedral octahedral sites. And only in the tetrahedral side you have enough screening, just because of the plasma oscillation of the D electrons, to reduce in a very substantial way the Coulomb barrier, which is a prerequisite, again, to have cold fusion. Now, the dynamical pathways of electrochemical loading, on the other hand, are different, okay? And these are, okay, here you have D pluses which go to the surface. They have the same evanescent field, and they have the same thing. However, now you also have the whole dynamics on the surface, just using electrolytical pressure, which changes the balance of the chemical potential. And this is why, with a lot of care, a lot of patience, and ingenuity, our two friends are the two founders, the people whom we should thank for being here, in fact, saw the way to go away from the fateful x equal 0.6 and to higher x, and then they were consigning to mankind such a fantastic bonus, okay? Now, then the dynamics here is governed by the surface chemical potential, double layers and all that, ponderomotive forces, everything that you can work out from the existence of this basic evanescent waves, which are related, which are associated with the coherent plasmas, okay? And now there's also a role for the Mach in avoiding that forms a kind of that forms at the surface of palladium, and avoiding D plus D plus DD recombination, and this is relevant to explaining the heat after that has been seen by Martin and Stan. As far as the answers for the nuclear physics, okay, well, then there is a calculation of the D shell, an approximate calculation. I presented them out, but now I have a student that is taking his degree in Milan and doing much better calculation, which is reproduced essentially quantitatively, almost quantitatively, what I've done. And this is just this screen potential. Now, people say, but this is too late, it's impossible. But this is not the real potential, the real binding energy for the whole lattice. This is just what kind of potential the deuterons see when they are sitting in a particular region. Of course, the question is that in that region, the electrons, in fact, are moving very fast in a plasma-like way. So their inertia is much higher because, it's like if you have a phalanx, this formation of Macedonian formation. If you want to knock a soldier of a phalanx, it's much more difficult to knock down. It's much more difficult to knock down a single soldier, which is not in the phalanx. So essentially, if you do understand why mu catalysis work, you must understand why. And this, I know that Peter Higginson finds this idea repulsive. Peter, study it because it's right. Certainly, if you have a single electron, of course he cannot do whatever you want. He cannot do better than any Fermi atom, Thomas Fermi atom. But if you have 10 to the 13 electrons which move in phase, if you want to meddle with this position, you have to meddle with the position of everybody else. And the system reacts in a very stern way. In other words, the real inertia of the D shell electron that is not the inertia of an electron, but the inertia of a collective plasma. So if you do have this means really that you have a lot of screening. And in fact, you have the gamma amplitude 10 to the minus 51 about, this is what refined people calculating the D2 molecule goes down to 10 to the minus 21, plus or minus 1. So again, I make a factor of 5 mistake by choosing inappropriate parameter. But the factor of 5, with respect to 10 to the minus 21, actually is less than the errors that this 10 to the minus has. So again, this is another mistake for which I've been condemned to, I don't know what kind of punishment, but condemned anyhow. So if this is all where there was, this about this screening in the tetrahedral side, you would have fusion rates on the order of a few per second per centimeter cube of palladium.
I hate to do this to you, but 5 minutes.
Okay. all right. So, okay. But however, this is not the main path. There are other paths. The most important path is this. This is enhanced because of a collectivity of the system and so on and so forth. You have to look at this. And then you do expect the energy release through this thing to be electron radiation, electromagnetic radiation of all frequencies, exotic photonuclear reaction. And here, Peter, there's some good news for you. You can have a photodisintegration of the deuteron and so on and so forth. So you have your neutrons going around, activating all kinds of things, and heat and phonons. But heat and phonons only at the end, not at the beginning. And okay, let me conclude that at this point, as far as I'm concerned, and I'm standing behind this, and crucify me, yes, but openly debating things, not really gossiping as usual, gossiping in the corridors or whatever, of the pathology of cold fusion based on the general laws, yes, the general laws of the loved and cherished quantum electrodynamics, a fantastic piece of synthesis of this enormous monument that I and Morrison, of course, love, and is called the Standard Model, okay? And in fact, the science of cold fusion is but the tip of the iceberg of a new science of matter. So finally, what's wrong with this? Okay, so this is what they say about my work. I'm imaginative, but miracles, blah, blah, but I violate also, and so on and so forth. I do not violate any laws of physics because actually I'm deducing these results from the basic laws of quantum electrodynamics. So that I do violate only the paradigm, which my critics still cling to, maybe for lack of better things. Okay? So, all right. I already replied to this critic about the screening of the d electron, and I say, all right, collectivity. Remember what can, the collective behavior do to the single act of emission of a gamma rays in the of a nuclide, of a Mössbauer nuclide, where there's no recoil just because 10 to the 11 nucleon, 10 to the 11 ions. Nuclei just share the recoil of a single act of emission. And now there's evidence even of stimulated Mössbauer effect, which is something really enormous. And also remember mu catalysis. So then if you do understand this thing, you must understand the relevance of this criticism. And there are others. So I've just come to the end. But let me tell you with all frankness that the most negative attitude that impregnates this community since 1989 is a kind of skepticism towards any theoretical approach on the ground that one has the feeling, the self-defeating feeling, that one does not possess the adequate intellectual tools to deal with the cold fusion phenomenology. I do not know whether I have been able in the 40 minutes of this talk to convince you in any way that it is time to change this attitude. Let me, just to end, use a different strategy. Now, following the strange implication of this general theory, I have embarked into an imagining of a new research line related to the Fleischmann-Pons electrolytic system. And I have estimated that in realistic configuration, there is the very definite possibility of attaining efficiency beyond 100% with power density in the order of 50 to 100 kilowatts per centimeter cube of palladium. And I believe that all this should come true by the time of ICCF-5. Thank you very much for your attention. Still have it with me.
I'm sure that. I think I will, since we have a discussion session tomorrow, I will just, and we are running massively behind time, I will take 2 questions. I know Scott Chubb had his hand up during the lecture, so I will let him, since he belongs to the group of solid state theory, I won't give you the next line. Gell-Mann, was it?
Yes. It's, after 5 years, I do think we are converging, which is rather interesting. I would point out, Juliano, that the solid state self-consistent theories are coherent theories.
No, they're only self-consistent. They're not coherent because they're not based on an approach. The self-consistent theory have this problem that, in fact, they go from explanation from the why to self-consistency.
They what?
They go from the why, based on the laws, to something that is self-consistent. If you take this potential, then it self-consistently works.
No.
Yes.
No, look, I agree with you, okay? If you start with energies that are greater than 0, everything you said is true. When you go to energies that are less than 0,
okay,
you have different things.
I think, I think we should make an absolute resolve something. No. Let's resolve something, that we really ought to have a systematic discussion at the next meeting on. Peter Hagerstein has my list of topics. I don't know who to take, Peter, could you make Dr. Stella wants, Dr. Filimonov wants to say, Bob Bush wants to say, is Peter here or has he left? Peter, are you taking a note? May I suggest we continue this discussion tomorrow in the slot? You obviously have David Nagel, lots of people want to come in. Give your names.
It'd be nice to discuss now. Can we not discuss now?
No,
Very
I
exciting.
don't. No, because we're going to
Look, he was sleeping all the time. Now he's inside.
No, listen.
Taking 10 pages of notes.
No,
Very
no,
interesting.
no. You have you have an hour tomorrow.
I haven't made any bad
you can
gesture,
cut-
though.
You can cut the viewing time of the posters, and you can extend the discussion tomorrow. You have it's not right for Dr. Lee, Young Kim, and so on to deprive them of their time. That is not right. We have an active discussion. Let's pursue it tomorrow.
Okay.
Right. Well, we have Professor Lee here, who is going to talk to us about the gamma. Where's Professor Lee? Here. What are you going to talk to us about? I thought you were going to revisit the gamma factor.
Yes.
Right. Good. Come, revisit it.
Okay. Thanks, Martin, to give me this opportunity, give me this 20 minutes. The subject is an attempt to solve the puzzle of excess heat without strong nuclear radiation. I have a long list to acknowledge the help I received in the past year. Particularly, I should say, without the personal contribution from the organizer of this conference, I could not be here. After 5 years or 6 years intensive studies, we have two facts are well established. The first is, under certain conditions, there is excess heat of the order of several watts per cubic centimeter. Its origin is non-chemical. On the other side, we all know there is no commensurate neutron, gamma, and triton. Almost all the theory start from this formula. The reaction rate equal to the reaction constant times the wave function squared. Everyone knows the Coulomb barrier suppresses this wave function to a very small number. All my friends remind me that, Lee, remember this. If you try to increase this wave function, you remember the muon catalyzed fusion. Because at such a low energy, the lambda is a constant, is proved by the experiment, and the branch ratio is still equal to 1. There must be some gamma radiation from excited helium. But the muon catalyzed fusion reduces the Coulomb barrier. The resonance penetration is different from the reduction of Coulomb barrier. The resonance means the wave function will build up during its bounce motion. If this reaction constant is strong, the damping is so strong, the wave cannot bounce a lot of times. It will damp after a few times, then there will be no resonance. So if resonance happens, this reaction constant should be very small. This means it's a weak damping. It's a long lifetime state. Can we see it? Nuclear physicists cannot see it because this is very narrow energy level. Their beam target interaction cannot see such a narrow energy level. Who can see it? Chemists, in terms of calorimetry. Let's look at heat after death data. This is the time accurate to 1 second, even better than 1 second. This is the temperature. Here is 100 degrees. It's accurate to millidegree. So when we see this data, it shows when the electrolysis stopped, no power input, the power output keeps going for 3 hours. It's 10 to the 4th second. This is a reliable number. Then we should ask, what is this state? The energy released in this period is about 29 megajoule per mole palladium. If all the deuterium stored in this palladium burns, the energy of combustion is about 148 kilojoule per mole palladium. So the difference is the effect of 20. So this is the energy of non-chemical origin. And the lifetime is 10 to the 4th second. It's a very long lifetime. But we may notice not only this experiment shows this kind of state. In another continent, in another system, it's a closed system, Dr. McCubre saw the heat after life. He didn't boil all the electrolyte to dry. He still saw the same phenomena. This is the current for electrolysis. And here, the current goes to 0, stopped. The green line is excess heat. We see a small peak. The small peak is here. This is the time scale. This one division is 24 hours. What's the width of this small peak? Just about 3 hours. It's 10 to the 4th second. Maybe you say this is a kind of noisy. Just ignore it. It's not a noise. Because the accuracy and the precision in SRI experiment is plus minus 10 milliwatts. And here this scale is 100 milliwatts. So there is an energy output, definitely in this time period. How much is energy? We can calculate based on this loading ratio. The deuterium available in this period for burning, we calculate from this loading ratio change. It's about 49 joule. We calculate this excess heat with the time period and the height. It's 442 joule. So it's an effect of 10. So this is a state releasing energy, non-chemical origin. It's a long lifetime, 10 to the 4th second. Yesterday when I listened to the talk given by Ed Storms, he talked about a phenomena that's replacing the deuterium in the electrode by hydrogen. He said, it takes time for several hours. The excess heat keeps going, even you try to put the hydrogen in. As I see, this is a hint of a strange state. That's releasing energy for several hours. You try to replace the deuterium. In fact, that's deuterium state in a nuclear active state. the lifetime is about 10 to the 4th second. Even more, the day before yesterday, I talked to my friend Biberian. He used the colorful crystal, single crystal. When he stopped the input power, he still see the excess power going on for several hours. Look at this picture, it's 3 to 4 hours. From my point of view, this is a state releasing the energy, non-chemical origin. The lifetime is 10 to the 4th second. So may I suggest all the experimentalists here, go back to your data for the excess heat. Maybe you can find more hint. It shows the non-chemical origin energy state. The lifetime is 10 to the 4th second. Now, that's the experiment say. What does the theory say? This is the lifetime for the excess heat. This is the mass. This A is the size of nuclear interaction, H Planck constant. The theta is the famous gamma factor, defined in a conventional way. In fact, Dr. David Thompson knows that when I wrote my first manuscript, I just derived this formula in a square wheel case without knowing this data. But now, my second manuscript extends this derivation to arbitrary potential configuration. So this is from the first principle. And when we put all this number in, it's just about 10 to the 4th second. How do we derive this? This is uncertainty principle. The lifetime of a state is h over the width of the energy level. And this width of energy level equal to this. This is the wave number real and wave number imaginary part. That's the identity. So this step go to this step, just using the resonance case, this real wave number equal to 1 over the A. So we put one more A here, we put one more A here. In order to prove this equation, we have to prove the imaginary part of the wave number times the nuclear size equal to theta minus 1. It's a very small number. I have proved this in my poster session rigorously, but physically, it's from the first principle, that's conservation of probability and the continuity of the wave function. So if we use this number, the mass is 10 to the minus 24th gram, A is 10 to the minus 13 centimeter, H is 10 to the minus 27. We use the theta number from Sadovich's calculation for the muon catalyzation. And from the Caltech Koenig's paper, just use 10 to the 27. Then we come to this number, 10 to the 4th second. Now, a lot of people will ask me, you have such a long lifetime, the energy level must be very, very narrow. How can you find this narrow energy level? I say, yes, it's very, very difficult if you use beam target experiment. Here is the Coulomb barrier, here is the beam. The beam has energy width. Just like use a screwdriver to detect a tiny crack on the brick wall. You cannot see this tiny crack. How can you see it? Use a needle. The needle is a trapped particle in a well. Then that's a needle. But if you have a bunch of needles, then you have more chance to detect this tiny cracks. what is a bunch of needle? That's the deuteron-ion energy band. Of course, you have to put enough population on this energy band. This is a kind of condensation. Experiment has shown that deuteron in the palladium act like an ion. That's a boson. We may expect a kind of boson condensation with some prerequisition. So, seems we can go this way, but we should make some prediction, then see whether the experiment can prove this. We have 3 predictions. First is the grain size. The second, the energy gap in the band structure. The third, there must be helium. The grain size determines how many energy levels in this narrow energy band. As long as you can keep the high loading, the greater the grain size, the better. The second, in order to have a condensation from the excited state to the ground state, we need a kind of energy gap. Based on the experiment data, we know the threshold for the loading ratio is about 0.885 or 1. Based on this kind of number and the density of palladium, we can calculate the width of this energy gap. It's about 160 milli-electron volts. We can measure this by the inelastic neutron scattering to know this number. The more important is if the material scientist can control this width. If the energy gap increased by a factor of 10%, then we can reduce this threshold to 0.6. Then the loading problem is much easier to be solved. So, grain size make excess heat will be higher. It's easy to do experiment. Energy gap control will reduce the threshold, make the experiment easier. So, if we can prove this, then we have better chance to improve the reproducibility. Of course, there is a key point in this theory. It's only for D-diffusion. Then there must be helium. So when I come here, I look for, yes, thank you. I look for Yamaguchi, look for Dr. Miles, look for Gauzes. I'm looking for helium. In fact, yesterday, Dr. Mark Kubrick talked about this formula. Fortunately, this model can explain this. Now, we come to the final page, that's conclusion. The conclusion is thunder without lightning is okay. I have 2 meanings. The first, we try to answer Professor Huizenga's famous challenge of 3 miracles. The first, because of resonance, we can penetrate the Coulomb barrier, and this resonance cannot be seen by the beam target experiment. Second, this branch ratio should not be equal to 1 because we are talking about a kind of slow interaction. It's not a strong interaction because strong interaction will kill the wave in several bonds. There is no chance to be in resonance. Then talk about the gamma. The helium should have the gamma, the electromagnetic radiation. It's a factor of 10 to the 6 weaker than strong interaction, but it's still too strong to be in resonance. So what we are talking about, the resonance, it's a kind of very slow interaction with a time constant 10 to the 4th second. But this is in resonance, So this lifetime is proportional to the theta first. In comparison, if we use gamma factor for the non-resonance case, this lifetime is 10 is theta to the square. So we win a theta factor by the resonance, and we can answer this question. The second point, this is a slow interaction, whether it's a practical energy source. Yes. The power density equal to how much particle can be in resonance over this time constant. If we put all this number in, the maximum number is about very close to first Faraday's number. It's 1 megawatts per cubic centimeter. So it's a practical, useful energy source. Thank you for your attention.
Well, I just have one point of disagreement. I think 1 megawatt per cubic centimeter.
That's the maximum number.
I think we have time for one question. Yeah, go
I
ahead.
don't want to be the only question, but tell me once again, what do you mean when I must find this very fine energy level? And if I'm experimentally doing something, what does it mean to find this fine energy level?
Thank you.
You want to fine-tune it, don't you?
Yes, I needed a fine-tuning. That's the fine-tuning. I will talk about this fine-tuning in the poster session by a self-lock mechanism. This is energy
fine-tuned.
Yes.
You can do this a lot of ways, I think, can't you? You could do this several ways.
Yeah, thank you for this important question. This energy level width is 10 to the minus 19 electron volts. It's very, very narrow. How can find this? At first,
Why do I need to find it?
if you do not find, there is no resonance. The resonance means the energy level in the lattice confined ion should be same in the energy level in the nuclear confined well. That's the resonance.
Yeah, but experimentally, do I? Yeah, still don't get it quite.
No, I think nobody gets it, actually. Because, I mean, I think one thing is whether nature allows it, one thing whether you allow it for your theory because you need it. The real question is that, you mean, this environment is so complicated, there are so many things. How can you keep anything to the 10 to the minus 19 electron volts? This gives me really, I mean, I could just faint here, you know, with this kind of thing.
Don't faint today, faint tomorrow. I think have we got on here? Yeah.
Where do I put that?
Mike. I've exhausted my goodwill. I don't think I had very much, actually.
Our next speaker will be Dr. Kim, and he'll be discussing uncertainties of conventional theoretical estimates, low energy fusion rates due to electron
Microphone? Yes. This is the one. Go agora.
If you want to do it around the back.
Yeah, otherwise. No. I don't want to step back.
Okay, you just carry it with you.
I will.
Yeah. Okay. Should do it.
I am supposed to summarize my own 5 abstracts, but it's impossible. Of course, in the poster session, you can ask questions about all of them, but I will concentrate first one. And title, incidentally, is not one I'm going to use. I will show you. But what I'm going to say has some relevance to earlier topic various speaker brought up. And I borrowed this view graph from Ed stone, but then I made a mistake of writing on it. Actually, that's what I want to write. But I'll touch on three-body fusion, which Professor Kasagi talked about, and few speakers before this cavitation fusion, and then possibly these. I'm not going to talk about it, but I'm going to say there's a relevance to what I say. So officially, my title of the talk will be Uncertainty of Conventional Theories, and is there room for improvement? And I'll address these difficulties based upon new formulation, which is based upon optical theory. And instead, I'll display all of the view graph in poster if organizer can clear out all of the papers. Well, conventionally, as you know, you get the gamma factor by doing this type of calculation. And I won't go through because I don't have time, and you know all that. But question is, can we improve that? So we start looking into a different way to formulate that. And I'm going to use a new formulation based upon optical theorem instead of WKB or other nuclear reaction theory or model theory, optical potential model. There are many, many nuclear reaction models, but this is drastically different from existing nuclear theory approach. If you take a two potential scattering problem, one can, I'm not going to go to derivation because of lack of time, but I'll answer all the questions at the poster or later. Essentially, you get the optical theorem, which is stated in here. And this is rigorous. Now, at a low energy, you can essentially drop the elastic cross-section out of this expression and get this expression. So what this means is that if you want to calculate the fusion cross-section, you need to know elastic, imaginary part of elastic amplitude, not the fusion scattering amplitude, fusion channel, but the elastic amplitude. So the question is, how well we know that? Of course, we don't know unless we can do some experiment. But meanwhile, we have to start speculating. How do I find out that part? And we can use this formula, which is still rigorous if you believe this Riemann-Schwinger equation, and end up with this expression. And of course, we do not know this imaginary part of optical potential. But we can show that it's separable. Proof is given in a paper we are publishing soon. But then you don't know the strength nor the range. And the crucial point about this formulation is that we are trying to study effect of nuclear force range or effective potential range in elastic, imaginary part of elastic channel. We do not know, but we can parameterize with some mathematical form with a one parameter range or series of it. But let's assume there's simple one term. Instead, if I take a different form, I still get the same enhancement factor. That is, it seems to be independent of the shape of the G function you assume. And the final result, we end up with this formula. Now, one difference from previous formula everyone is using is that there is this exponential factor, which appears to be quite universal and comes with a positive sign in the exponent. Now, that means as you go low energy, it will become larger. And in fact, there are some experimental data which suggest that. For instance, this is a very important reaction cross-section for astrophysical problem. And no one can explain this rise. The electron screening effect only gives this much. So initially we developed this theory to explain that, but then we realized that this can have an implication for cold fusion. So let's compare with the conventional formula, which is given here. This is gamma factor everyone is using. And then we have a formula here which has this enhancement factor. And that enhancement factor, it has this form. And it can increase toward low energy. And in particular, if beta is very small, beta small means it's a longer range. Then, even if this strength is weak, if beta happens to be longer range, you can cancel gamma factor almost nearly or completely. But of course, we don't know that. This is speculation yet. We try to prove from theoretical derivation that one can have a long-range interaction in the imaginary part. So far, we haven't succeeded mathematically. But there are examples in other areas of physics where long-range force arise from various sources, mostly due to Coulomb interaction. One of them is called electric polarization potential, which goes like 1/4 power. Another one is called Efimov effect. I won't discuss this detail. Another most relevant one is this imaginary one. And this comes about if you try to get the effective elastic scattering potential from Coulomb excitation type reaction. And this goes like 1/5 with a negative sign. That's the attractive long-range force. There are known cases, but we do not know whether we can prove this for the fusion reaction case. We are talking about elastic potential.